Today we're talking about mutually exclusive and independent events along with sample space. So a little bit more to add on to the whole probability unit that we're dealing with. And we're going to find the probability of these respective events. You'll learn about the definition in the sense of like math and like use the math to determine if events are independent or if they are mutually exclusive. Okay? We are going to start with mutually exclusive and then we'll do independent and then we'll wrap it up with sample space. Just as a heads up, we're pretty much coming to the end of this probability unit, so you guys are going to have a test on the 6th, so that's next Thursday. Okay? Let's give you guys a heads up next Thursday. So, two events are known as mutually exclusive if whenever one event occurs, it's impossible for another event to occur. Okay? Mutually exclusive, also known as disjoint. Okay, so they can use either mutually exclusive or disjoint. They mean the same thing. Basically, when one event occurs, it's impossible for another event to occur. Okay? For example, say you toss a coin. The event of getting a head and the event of getting a tail at the same time is impossible. Okay, and we're not considering landing on its side or anything like that. Okay, that's an example of a mutually exclusive event. Okay. Now, the thing to know algebraically if events A and B are mutually exclusive if and only if the probability of their intersection is equal to 0. That is in your reference booklet. Okay? So if it ever asks you to show or determine if two events are mutually exclusive, that's what you'll basically need to prove, to show. That their intersection, the probability of their intersection is indeed equal to 0. Okay? And there's a Venn diagram that goes along with what mutually exclusive events would look like. So, this particular example, okay, it says a card is selected at random from a bag, okay, and the cards, they're all equally the same, and, you know, none is like, one's bigger than the other, nothing like that. But the cards are labeled 3, 4, 5, 6, 7, 8, 9, and 10. So, we're going to let A be a prime number. We're going to let event A be us picking a prime number from this bag of these cards. And we're going to let event B be an even number is being chosen. So, let's draw a Venn diagram to represent this particular situation, and then we're going to determine if events A and B are indeed mutually exclusive. So, your Venn diagram, of course, you know we need our sample space. Anytime we draw a Venn diagram, we always have to have our rectangle. All right? And out of the cards that are listed here, let's kind of go ahead and let's figure out which one of these cards is a prime number. Anyone?
5,
5,
7,
7,
3.
3. Any others?
No.
Okay. So event A is circled in blue. Okay? And let's go with event B, an even number.
4, 6, 8, 9.
And 10. 9, not so much. Okay? So, we're going to have A and we're going to have B. But if you notice, do A and B have anything in common?
No.
No, they don't. So what's going to go solely in A?
3.
And solely in B? And in the universal set? 9. Okay? So this will be the Venn diagram that you would draw. Would they accept an overlapping two circles where the inside is not, there's nothing on the inside? There's a strong possibility. Okay? Because then technically you are still showing that out of this particular event that's happening or experiment that's happening, they don't have anything in common. Okay? So what is the probability of their intersection?
0.
0 out of?
1, 2, 3, 4, 5. You asking all the numbers or all the possibilities?
Out of 8, out of the numbers that are in the card. So clearly 0 over anything is 0. Simple as that. Even just drawing a Venn diagram, you can see they have nothing in common, so you know automatically the probability is going to be 0. Simple enough, yes?
Yeah.
Cool deal. Go grab a whiteboard. Alright, now, when the occurrence of one event does not affect in any way the occurrence of another event, then the two events are known as independent of each other, mathematically independent of each other. so we have the issue. If one event, the occurrence of one event has no effect on the other, then they are known as independent events. Okay? And A and B are independent if and only if their intersection, the probability of their intersection is equal to the probability of A times the probability of B. This is the formula that you would use to show that two events are independent. So you basically find the probability of their intersection, and you see if it equals the probability of A times the probability of B. And we're going to look at an example of this. All right, here's our example. Back to the bag that has these cards: 2, 3, 4, 5, 6, 7, 8, 9. A is the event an odd number is chosen. B is the event that a square number is chosen. We're going to draw a Venn diagram to represent this, and we're going to determine mathematically whether or not these two events are independent of each other. Now, some of them, again, can kind of be like a little straightforward, but anytime you're trying to figure out if something is independent or mutually exclusive, please try to support it with the math. Okay? So, of course, we need our universal set. An odd number is chosen. A square number is chosen. Let's go through this. What are our odd numbers?
3, 5, 7, 9.
We got 3, 5, 7, and 9. What are our square numbers? 4 and 9. So as we can see, there is an overlap. Yes?
Yes.
So that means these two bubbles. I'll change the colors. In the middle, we're going to have a 9. What's going to be just in A?
3, 5, 7,
What's going to be just in B?
4,
What's going to be on the outside?
2, 6, 8, 8, 2.
So there's the Venn diagram that basically represents this information. Now we're going to determine if they are independent of each other. Remember, to be independent is the probability of their intersection has to equal the probability of A times the probability of B. Well, the intersection, what's the probability?
1 out of 4, 6, 5, 7, 6.
Intersection is
1 out of 8. 8 numbers there. We have to make sure that that equals the probability of A times the probability of B. A, how many are in A? A, 4. Not just A, but A total. There's 4 out of 8. That's the probability of getting a number from bubble A. What about B? What's the probability of B? 2 out of 8. Okay? So, I need to see if 1/8 does indeed equal 4/8 times 2/8. When you multiply these, what do you get? You get 8 over 64, which is indeed 1 out of 8. So, are these events independent?
Oh,
Yes, they are. Does everybody see how independence works?
That means that, so whenever it says independent, it means like one can happen without the other happening.
basically
That's just a
having one happen
special little rules.
that happen the other one.
Mathematically. That is the formula for combined events. So you already have this first part, that's 0.8. You have this part, that's 0.5. You have this part, that's 0.6. The thing you don't have that you want to find is that. That's 0.8 equals 0.11. When you subtract, that's a negative 0.3.
Treat it like X, right?
Yeah, you're basically treating that like X. So your answer for A is 0.3. Because you divide by a negative 1. Good job.
Yes, Jalissa.
Now this right here, yes, this represents conditional probability. In your formula booklet, in your reference packet, it says conditional probability. That's the symbol is there. It is right there. It says the probability of this intersection all over the probability of A or B.
Yay.
B. It's always the part that follows the bar. So even if these were mixed up, if they were backwards, it still would be the intersection at the top, but the bottom would have been the probability of A. So you take your answer to A, you divide it by a probability of B, and that equals 1/2. 0.5. Now, C says determine whether they're independent and give a reason. When it says give a reason, that is where you do the math to support whether or not you're saying yes or no. So you need both of them because this is one of those, you get an accuracy point for saying yes or no, and you get a reasoning point for your reason, but you don't get both if your reason sucks. Okay? So, their intersection is 0.3. We need to see if it's the same thing when you multiply the two. That is 0.5 times 0.6. What is that?
0.3.
So, are they independent?
C, senor. I got C right.
Yes, independent. If you want to do a complete sentence, you can do that. Yes. It's up to you. It's going to be the same thing. Yes.
I think it's important to note that I did get C right.
Last thing, sample space. Okay?
Oh, baby.
A sample space diagram is a graphical way to show the possible, equal, likely outcomes of any experiment. Do I expect you to write this down? No, I do not. This is, you can write down definition, but the picture, that's just an example of what a sample space can look like. So say there's two things that are happening, you're rolling two die. You have the outcome of the first die, you have the outcome of the second die, and these are the different combinations that you can have. Okay? So a sample space, it could be the numbers actually listed, or it could be dots, like in their respective places. So it's just a visual to help you when you're trying to determine your probabilities. Okay? So in this particular experiment, if I'm rolling two die, how many outcomes? What are my possible equally likely outcomes? How many do I have? Yeah, 36. Okay. So if any type of question that involves rolling two die, two regular six-sided die, and you're trying to figure out different probabilities, and it's not conditional, your total amount will be 36. Okay? So we're going to look at one example with this, and that'll be it for today. Okay? A red die and a blue die are rolled together. Calculate the probability that the total score is 7. So basically these are basically still six-sided die, just one is red and one is blue. So 1 through 6. We're going to calculate the probability that the total score is 7. The same number comes up with on both die. The difference between the score is 1. No, I had to see these backwards. And the score on the red die is less than the score on the blue die. Okay? Something like this. A sample space would be very helpful. Okay? So look at this. Make this one your red die. Okay, so all these are red. Make this one your blue die. It's just another visual to kind of help you out. Alright? So, the first question says, what is the probability that the total score is 7? How many of these outcomes have a total of 7?
2.
Alright, let's figure this out. Count in your head so we don't throw anybody's counting off. So, how many of these have a sum of 7?
6.
There's 6. So it's going to be 6 out of 36, but you can leave like that. If you want to reduce it, you can. Questions?
No.
Okay. Now it says the same number comes up on both die. The same number comes up on both die. Come up with your numerator, figure out what your denominator is, but don't say the answer.
So that one's a typo. Second, 2, 1.
Yeah.
I thought there was just 2, 2, 1. No, that makes sense. Yeah, it did.
Alright. So how many?
5 over
6.
6.
Over
6.
16.
Over what?
36.
Yes, 6 over 36. Good job. C. The difference between the score is 1. The difference between the score is 1. The difference is 1. That's here. Here. As well as.
Okay, see,
Yeah.
it's a technicality. You have to define whether or not that counts as one in order for.
I wasn't that
You guys
makes
just
sense.
took a chance. There's an equal chance of you being wrong.
But the thing is about this
Yeah, right.
particular one, listen, the thing about this particular one here is you have a red 2 and a blue 1 versus a red 1 and a blue 2.
Right, but if we're looking at it from left to right, if we're looking at it numerically, then that could be considered a negative one, which is why
They're all equal.
five.
They're two
But
different.
the difference between the two numbers is still 1.
So understandable, but
Right, but if you have a 2-1 and a
Because
1-2,
the like the order
but
of red or blue
you have
dots
to
doesn't matter.
clarify. My point is that you have to clarify.
Not necessarily.
I think that you need to. I don't think there's
But
like
I
a
feel
there
that.
is
But
enough.
Alright,
let's say you get.
The score on the red die is less than the score on the blue die. The score on the red die is less than the score on the blue die. Your answer
I
is
got like 4 different
it is 15. It is 15. It's a lot easier when, of course, the paper is like right there in front of you and you can actually count out on your board, okay? So again, a sample space is just another way to basically provide a picture for you. Just like when we first started doing probability and we listed out the hesitation